I hope I am live now. Can anyone confirm if I'm audible or not? Hello? 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 I believe I am audible now. And probably in that case, I will. Okay, thanks. Raj. Hello everyone. Today we will be discussing Code Forces Starters 113. I will go through all of the problem except last two problem. Counting is fun and trees are fun. Let's get started from the easiest problem. The easiest problem is thala for a reason. You are given an integer n. Print thala if n is 4, otherwise sad. And we are given an input format. The solution is we will we should use to if one if else to find if n is 7 or not and print the corresponding string accordingly. So my code pretty much looks like it in 10. It's input using cn. If n equal to 7, print thala, otherwise print static. And moving on to the next problem, make 0. You are given a positive integer n. In one operation, you can either subtract 3 or subtract 4 from n. Can you make n 0 by performing any number of operations? Now there are some test cases and few things over here. Like to take an example, we are given that it's not possible to make n, but it's possible to make 3 and it's possible to make. In the problems like this, let's first try to see if the some initial values can be created. Like because 1 is less than 3 and 4, it cannot be created. 2 is less than 3 and 4, it cannot be created. 3 can be created. Like if we subtract 3 from 3, we will get 0. For 4, if we subtract 4 from 3, we will 4 from 4 we will get 0. For 5, we can verify that it is not possible because like either we can make 3 or we can make 7, or the next possible number we can make is 6, which is 2 times. So we will be able to make 6, which is 3 plus 3. We would be able to make 7, which is 3 plus 4. We would be able to make 8, which is 4 plus 4. And now looking at these initial values, what we can notice is that we have got 3 consecutive yes over here. So anything we make after that, like for 9, we can now we can have an induction on the value over here, or like whatever we want. Like for like because these are consecutive numbers, if we start from any large number, let's say 100, we can keep subtracting 3 from it, 94, so on, until we will get let's say 10 and 7. Then we will reach here and it should be possible to make. So the answer is if n is 1, 2 or 5, no, otherwise print yes. Any questions on this one before I move on to the next problem? Or I can probably move on to the next problem and you can ask questions related to it if any. The next problem is you are given an array A consists of n positive integers. Check whether there exist four distinct integers I, j, k, l such that I is less than j is less than k is less than l is less than n, and ai plus aj is not equal to ak plus al. And now let's look at some examples over here to understand what it is asking to us. For example, we are given 3, 4, 2, 5. Here we don't have any choice. Like I should be 1, j should be 2, k should be 3, and l should be 4. And in this case, I plus j is 7 and 2 plus 5 is also 7. Let's take any random array over here. Oh, sorry, I missed. So the problem asks us to find whether we can choose some I, j, k, l. One of the sample is 3, 4, 2, 5. And if here we don't have any choice, I must be 1, j must be 2, k must be 3, and l must be 4. And in this case, we can see that 2, 3 plus 4 is equal to 2 plus 7. So the answer is impossible. Now let's pick some random array. 3, 5, 2, 7, 6, 4, etc. So our ask is we should pick some four indexes from it. Let's say we have picked these three, and we are asked to say like, is can we find any such pair where the sum of first two is not equal to sum of last two? The idea is if let's say everything is equal over here, all the index are equal, then no matter what we choose, like the sum of first two elements would always be equal to sum of last two elements. It's a div 3 problem, sum not equal to problem. Yeah. So if everything is equal, then the answer is definitely no. If n is equal to 4, then we don't have any choice. Like I must be 1, j must be 2, k must be 3, and l must be 4. So we should just check sum of first two elements is equal to sum of last two elements. If the answer is yes, we should print no, otherwise we can print yes. Otherwise, if n is greater than 5 and there are at least two different elements in this array, one of the claim is that we would always be able to pick two such elements, like two such pairs, without loss of generality. Like if we can prove it for n equal to 5, then we would be able to do it for the rest of the elements as well. So for example, we have a1, a2, a3, a4, a5. And let's assume that there are at least like all of these are not equal. In this case, let's verify like if a like let's first compare all the pairs with a1 and a2. Let's compare all the elements with a1 plus a2. The other possible choices we have is a3 plus a4, a3 plus a5, a plus 4 plus a5. If this sum if this sum is not equal to any of like these, then we have definitely found one answer, right? Otherwise, we will have the case that all of these are equal. In this case, what we can see is if these two are equal, this implies a4 and a5 are equal, and if this and this is equal, it implies that a3 and a5 are also equal. And now let's also compare, like we have one condition like a3, a4, a5 are equal. Now let's also compare a1 plus a3 with a4 plus a5. If this is equal, because we already know that a3, a4, a5 are equal, we can cancel out this over here and we get a1 equal to a5. And if we also compare a2 plus a3 with the other element, because a3 is equal to a4, this also implies a1 equal to a2. So what we have found is if there are 5 elements and if there are two different elements in them, like let's say x, x, y, x, x, then we will be able to find one such pair between them, because we will have a contradiction over here. Like we initially started with not all of them are equal and then we came up with the conclusion. And if there are more than 5 elements, what we can do is if everything is equal, then the answer is definitely no, we won't be able to find an equal sum. Otherwise, we can choose any random 5 elements from that array such that there are at least two different elements from them. Like for example, we have 1, 1, 2, and we can just choose any 5 element over here. And we can try to solve this problem for these 5 elements. And because we have proved earlier that if there are five elements and if there are two different elements, then we will be able to find different pairs. The answer is also yes for this case. So any questions on this one before I move on to the division problems, like other division problems? Now moving on to the next problem, like maximum sum I am coming with. I am going in the same order in which the problems were given. Maximum score, yeah. Like maximum score, yeah, this is the one I am discussing next. You are given a binary array A of even length. Initially, your score is 0. You need to perform following operation exactly n by 2 times. Choose an index I, add AI minus absolute value of AI minus AI plus 1 to the score and delete both of the elements from A. Concatenate the remaining elements of A without changing the order. Note that after each operation, length of A decreases by 2. And we have to find the maximum score we can get if we play optimally. Like, let's see like what is the problem statement asking us to do. Like, let's pick a random string over here. Like, let's see what is the answer if all of the elements are equal. What we can see is that if we pick any two numbers, the difference between them will always be 0. So our final score will also be 0 in that case. And let's see like if all of the elements are 1, then also final score is 0. Let's say we have a random string where there are both zeros and ones present in it. And what we can see is like because there are both zeros and ones, there would be at least one zero which has one near it, at least one place where there would be a zero near one. Because if the first index is, let's say the first element is 0, there would be some ones, and there has to come a 0, then only the string will contain a 0 over there. And if the first element is 0, then there can be some sequence of 0, and there must be some place where there is 1, then only the element should be equal. So what we can do is we can choose this index, and the difference between them would be 1. We can delete it, and we can join the rest of the parts. And let's say this string contained 5 ones and 6 zeros. Because we have deleted only one pair over here, we would be left with 4 ones and 5 zeros. And as long as there are both zeros and ones present in it, we would be able to find an index like this. So, so like if we start with 5 ones and 6 zeros, after the first such operations, we would have 4 ones, 5 zeros. And then we will like once any one of them becomes 0, we won't be able to find any score over here. And this gives us a solution that we should count the number of ones and number of zeros and print minimum of number of ones and zeros. So any question on this one before I move on to the next problem? Like the final answer is count number of zeros, count number of ones, and print the minimum of this value. Okay, moving to the next problem now. Minimize the maximum subarray sum. Here we are given two positive integers x and y. We have to consider an array which has x number of ones and y number of -2. We can arrange A in any order we want, and we have to rearrange in such a way that the minimum of maximal sum over all subarrays is minimum possible. And we have to just hello. So what we are given is we have x number of ones and y number of -2, and we have to arrange A in any order such that the minimum of maximal possible sum over all subarrays of A is minimum possible, and we have to just print that value. So like let's see like what does it means. Let's say we have 3 ones and 7 -2. Then we can arrange it. One possible way to do is this way. And what we can, if we try to find the maximum possible sum over here, it would be these 3 ones together. Otherwise, if we pick any other subarray, let's say this, the answer is sum is -5 over here. The answer sum is 0 over here. So the maximum possible sum in this array is 3. And like overall the maximum possible total sum over here would be x minus 2 times y. And because there would be a place where we will have an index 1 as well, like because x is greater than equal to 1, like whatever we place there we will have at least 1 somewhere over here. So the maximum sum is at least 1. And now what I did here was, if we look at the places where we have kept -2, like if there are y is 4, then there would be 4 index where we will place -2. Like if there are 4, then 1 second. If there are 4 -2, then there would be 5 places where we will do it. And what we can try to do is we can keep equal number of ones over here. Like if we start by placing 1 over here, 1 here, 1 here, 1 here. Now because we have run out of time, we can keep the next one here. And if we look at it, like this would be one of the optimal answer over here. Or other way around, if we look at it, if we have kept 3 1 over here, it would be minus sum is 1. This will also contribute sum as 1. This will also contribute sum as 1. And this will contribute sum as 3. And its value is 6, which is also equal to the total sum of the array, which is 9 into 1 minus 38 second. 12 into 1 minus 3 into 2, which is 6. So the idea is if number of x is greater than equal to 2y, then the answer is maximum of 1, like the 1 comma x minus 2y. If x is greater than equal to y, we can also x is greater than y, then the answer would be 2, y plus 1. Yeah, the answer would be 2, otherwise the answer is 1. The way to do it would be, In this case, the answer is just sum of everything. In this case, what we know is that there are y minus 2s and there are y plus 1 gaps between them. And if x is greater than y plus 1, then there will be at least one gap where we will place two ones together. And for the rest case, the answer is simply that there are minus 2's more and the gaps between them is less. So some of the gaps will have 0 ones, some of the gaps we can keep 1 1. And that was the idea we had. So minimize the maximum sum, like the code is same as well. Like I first tried to find sum. If the sum is more than 2, I just printed the sum and continue. Otherwise, I just looked at like what is the maximum number of gaps we have and number of ones we have, and I tried to find the maximum one we can do. So here that can also be found using a ceil function. Now, if there are questions you can ask, or I will move on to the next problem in the chat. The next problem says you are given a permutation P of length n, and for each prefix, okay, can you re-explain the approach only? Like the approach, the way I looked at it was like we can always choose the complete array as a sum, and sum of complete array is n minus 2y. So like one of the sub, irrespective of how we keep elements over there, one of the sub array, like the complete sub array has this as a sum. And because we are keeping ones and two, we have a choice to pick, like we can also pick a single array, sub array of size 1 where there is only one. So the answer is definitely this is the lower bound. So the idea was if the sum is more than 2, print the sum, and if the sum is 1, then print 1, because we can always take the complete subarray. Or 1 second ago. Then I looked at the gap between different minus 2's. So let's say if there are 3 minus 2, then there are 4 places where we can keep gap ones. So like I tried to find the maximum number of ones we can keep over here. And that was x by y plus 1 ceil function. And I just printed this. Give me a minute. I will move on to next. Now moving to the next problem. Count distinct subarrays. You are given a permutation P of length n. For each prefix I, consider the prefix subarray P1 to Pi. Perform the following operations on A and possibly 0 number of times. Select 3 distinct indexes I, J, K, L, such that J is less than K is less than L, and AJ is greater than K, AK, and KL is greater than AK. Okay, like if x is less than equal to, which means 1 minus 2 1 minus 2 minus 2. Yes, the optimal answer is 1 Raj in that case. delete AK from the A and concatenate the remaining elements without changing the order. In case you want to perform more operations, you will perform these on the updated A. Find the number of distinct arrays A that can be generated through operations. Since the answer might be used, print it modulo this function. Note that the permutation of length n consists of all the integers from 1 to n in any order. Input format and all is given. Like, let's pick the sample over here, 4132. So we have 4132, let's say. What we are given is we can choose an index. In that case, one is the possible way where, like, or probably let me try to take some general example. And some more elements are there. What we can do is, in one operation, we can choose 3 indexes. Let's say, and if this is the case, which is not the case here, so it's invalid way to choose it. But let's say if we have picked some other combination, what we can see is 5 is less than 3 and 3 is less than 7. So in that case, we can delete 3 from this array. And we can do it again with the 2 as well if we want. It's our choice. We can delete it again. And we would be left with 5, 6, 7. Or what we can have done earlier is, instead of picking 3 over here, we could have picked 2 and 7. And we could have deleted it as well. So one thing we can see is, if we fix the numbers which would remain at last, like let's say there are, like this is the original array, and let's say that if we want to delete this, the best possible way would be to do is delete the smallest number between A2, A3 and A6 first, then second smallest second, and the third smallest number in them as the third delete operation. If we do it this way, then we won't have any conflicts or anything over here. So now coming to the solution part, the way to do it would be, for each prefix, find the indexes that can be deleted on the first operation. Like for AI can be deleted if there is some element which is larger than I from 1 to I minus 1. Sorry, if I keep it, let's say we want to do it for prefix L, to AJ, and there is some element which is greater than AI which is in I plus 1 to J, then we can delete AI, and like we can first try to delete all the elements smaller than AI whichever we want for the final configuration, and at last delete this element as well. So the number of ways to do it would be, like in the prefix A1, A2, A3, AJ, if we can delete 4 elements in the first operation, the number of possible final configurations would be, 2 to the power 4. So what we should try to do is, for each index I, find the nearest element which is greater than AI in the prefix, and similarly find the nearest element which is greater than AI in the suffix. And let's say the nearest element for AI is AK over here and AL over here. Then what we can see is that for any prefix which starts at L until N, we would be able to delete AI if we want. So the answer would simply be, then for each prefix, the answer is number of index that can be deleted and 2 to the power that. And now we can find AK, AI, AL using a monotonic stack. Like you can try to solve a block of 1 second. Like yesterday, someone created a block on code forces for that. So basically, monotonic stack. Like I will add a code, like someone yesterday created a code forces blog on it, like CF step was the channel name. I will share the video. You can visit it to find how can you find the nearest element like K and L over here. And like now moving on to the code part. First I found K and L. Like using stack, I created two arrays: larger number in the largest number before it and largest number after it. And I ran a for loop finding using them using a stack. And then I just like I added, like in case of K and L, like I just added the count which can we can start deleting over here, and then iterate over all of them and multiply by whatever numbers that can be deleted up to that, and at last print all of them. So any question on this one before I move on to score sum? Like I overcomplicated this problem. Like like if you try to print 2 to the power x, it can be the case that you had some int overflow or something. The other reason would be your x is wrong, like you calculated the wrong value of x. Your algorithm can be wrong as well. So here we are given an array b of length n. Like first we have defined some functions known as f of b, which is defined as for an array b of length m. Suppose f of b is I to m minus 1 to the power I plus 1 and absolute difference of bi minus bi plus 1 to the power 7. And now what you have to find is, you are given an array of length n. Find the sum of f of s over all non-empty subsequences of a, and since the sum can be large, print it some modular value it. And we are also given an example. For example, we are given 1 and 3. Then the number of distinct sequences can be 1, 2, 1 and 1, 2, 3. And in this case, for an array of length 0, the answer is 0. For 2 is also 0, and for 1 and 2, the answer is minus 1 to the power 2, 1, difference of 1 and 2, 1 and 3, and which is 128. Like these are the indexes, not the value over here. So if I try to summarize the problem, if we are given an array b2, b3, let's say bk, then what we have to find is and so on. And if you notice, we can even split this sum over here. Like we can try to find the number of arrays which have b1 and b2 as a difference, and then whether the sign is plus or minus before it, and we can find the answer based on them for each pair. So one brute force way to do it would be fix two indexes bi, bj, and assign plus minus before it, and count the number of sequences which have plus bi minus bj to the power 7, and number of sequences which have bi minus bj to the power 7. Multiply it by this and then add overall sum to it. And now let's say we have decided that we have picked bi minus bj to the power 7 and assign plus towards it. And say there are x elements before it and y elements after it. We have the number of choices for y on the part after it is 2 to the power y. Like whatever you choose, the sign would remain same for this element. And if you want a plus sign over here, the number of elements you choose over here should be odd. And there are total 2 to the power x ways, and number of ways to choose odd would be 2 to the power x by 2. If x is greater than equal to 1, and only one way if x equal to 0. Similarly, if we try to find the number of sequences which have a negative sign over here, like it would remain 2 to the power y over here, and it would be 2 to the power x by 2 if x is greater than equal to 1, and 0 if x equal to 0. And if you notice something over here, like the number of sequences with plus sign are equal if x is greater than equal to 0, 1. So like this sum would cancel out over here if x is greater than equal to 1. And x is equal to 0 only for I equal to 1. So in the end, whatever remains is b1 minus bi to the power 7 into 2 to the power y for each of them, and where y would be equal to n minus I. So the final answer would be b1 minus bi to the power 7 into 2 to the power n minus I. Sum of these, and we can do it using modular arithmetic. Any questions on this one before I move on to the next problem? Now moving to the next problem. Okay, I will have to also make a zoom equal. Moving to the next problem, it says you are given an array of n elements and a positive integer m. You can perform the following operations on A. Select at most m elements of A and increase all of the selected elements by 1. Find the minimum number of operations required to make all elements of A equal. It can be shown that for given constraint, it is always possible to make all elements of A equal using finite number of operations. Like, let's see, like, what does this problem statement mean? Like, for example, if we start with 1, 2, 3, and we can choose at max 2 numbers at every operation, and we can increase by 1. And we want to make everything equal over here. So one way to do is it, first choose 1 and 2, increase them by 1s, and then choose only 2 and increase it again. So in 2 operations we would be able to make everything equal. Similarly, if we try to pick 1, 1, 2, 2 and at max 1 element in one place, then we would need 2 operations. And let's pick some other element over here. And let's say we can pick only 2 elements at max once. And what we should do is we should always try to pick the smallest possible, like we should never make any element more than the maximum. And we should always pick the smallest elements whenever we are trying to increase something. So in this case, the way to do it would be, this would be one operation, this would be second operation, this would be the third operation, this would be the fourth operation, and this would be the fifth operation. And one more thing we should notice is, like, we will have to increase the smallest element max minus min times. Like if you notice here, we increased 3 5 times to make it equal to 8. And the answer is just the maximum of both of these. Let mx be the maximum in A, mn is minimum in A, and S is sum of elements of A. And we will have to increase minimum by mx minus mn times. And we will have to increase total elements n into mx minus s times. So we can try to do a ceil function over here. And the answer is maximum of both of these. To summarize again, like based on the sum of elements, the minimum number of times we will have to do operation is n into mx, because we want to make everything equal to mx minus their current sum by m, and the smallest element will also need mx minus mn times increase. So maximum of both of these would be our final answer. So any question on this one before I move on to the next problem now? So moving to the next problem, maximize the minimum. Although I did made a lot of observation on this one, I was not able to complete it within time. Like any proof Like if you do it, it will always work. Like proof by AC is probably I can say. Like because like it's mostly a greedy idea only. Like because if we increase max, then we will have to increase all of the element to that element as well. So if you change max to let's say max plus one, then we will have to make all the other elements as max plus one as well, which will increase the total sum by n and increasing the overall elements. And because we can also choose elements less than m at each point of time. So if we have less, like let's say we have to make final sum 8 and there are only three numbers less than 8, we can just choose them and try to increase them. And because we can choose any order we want, we would be able to make all of the elements at equal, like at last was the other proof. You are given a binary string s of length n. Let f of x denote the longest non-increasing subsequence of binary string. Your task is to partition S into two disjoint non-empty subsequences S1 and S2 such that minimum of f of S1 and f of S2 is as large as possible. Find the maximum value of minimum of f of S1 and f of S2 for that you can get. Like there are way too many definitions over here. So let's simplify the problem statement one by one at first. Like first, let's look at what is f of s. We are given that the string is binary string and f of is longest non-decreasing subsequence. So because it's a binary string, there are only two possible, like the longest non-decreasing sequence will look more like this. There will be some set of zeros and then there will be some set of ones. And by we are also given that we can partition two. So by partition here means we have to divide this string into two different sets. Like one of the set can be let's say S1, S3, S4, S5, and the other set would be S2, S6, S7, SK, and things like this. Then we try to find the longest non-decreasing sequence of this, and then the longest non-decreasing sequence of this. And like we try to find the length of both of them and we take minimum of both of them. A working example, let's say this is the given initial string S and elements in blue are S1 and the other elements are S2. And if you try to find the longest non-increasing sequence, it would be this sequence only of zeros, one. And the longest non-increasing sequence, like I added way too many zeros, so it would be 3 as well. And the minimum of these two is 3. So the final value for this partition would be 3 in that case. And if we change this string, like in this case, the longest increasing sequence would be 0, 0, 0, 1, 1, 1, 6. 0, 1, 1, which is 3. So the answer is again 3. And if we look at now, look at the initial string. The initial string S1, S2, S3, and if we look at here, this was the cutoff where we pick everything, all the zeros before it and all the ones after it. And if we compare this string as well, like it has this cutoff point where we have picked all the zeros before it and all the ones after it. And what we can prove is, like, there would be, for any string, binary string S, there would be some cutoff index such that we pick all the zeros before it and all the ones after it. That cutoff can even be the last index or the first index. So if we divide the original strings into two sets, there would be two cutoff index corresponding to both of these. Let's call the cutoff index for one of them as I1 and the other as I2. And without the loss of generality, like, we can always assume that I1 is less than equal to I2. If that's not the case, we can just make the smaller one as 1 and the larger one as 2. Like, we can just swap them. So we have some string S4. What we are given is, we should always pick all the zeros before it for the first string, and for the second string we should pick all the zeros before this and all the ones after it. So let's say if there are Z1 zeros over here and O3 ones over here and Z2 zeros over here and O2 ones over here, then the LIS of the first string is Z1 then we have a case where we have Z1 zeros over here, we have Z2 O3 and Z2 zeros in the second part, and we have O3 ones in the third part. And we can try to do one more video over here. Let's say if we have picked 0, 0, 0 from this part, and if we pick these as the starting index for the first string and these are the starting index for the second string, then we can also swap these zeros to make this string look like this. Thereby making it as small as possible. Similarly, we can also do something like that over here. So, like, that's the main idea. Like, if we try to make A1 as small as possible, because we know that in this part we would give all the Z2 zeros to the second string and all the O2 ones to the first string, and here we will try to divide all the ones to both of the strings. So now the main part is, because we want to find the minimum, we can also binary search for the minimum. And let's say if we want to find S1 and S2 such that f of S1 is greater than mid and f of S2 is greater than equal to mid. And let's say we also fix the number of zeros we want in the longest decreasing sequence of S1. Let's say the number of zeros in longest decreasing sequence of S1 is X. So the way to do it would be, Pick the first x zeros and pick the all the ones nearest all the ones after this mid minus x. Take it as s1 and find the longest decreasing sequence of remaining string. Like put everything to the s2 and find the longest decreasing sequence of that part. That also turns out to be greater than mid, then the answer is yes. We can make f of both of them equal to greater than equal to mid. Otherwise, we won't be able to do it, and that will be the main binary search for this part. And we would be able to solve all the values for it, find the final value for it. And this pretty much completes like all the solutions or all the solution ideas which I wanted to discuss for this contest. Like because I haven't solved the last two problems, I don't know how to solve them. So if there are any questions in the chat, I will pick them up. Otherwise, I will probably end this stream now. Thank you everyone for joining.